Okay guys, let's take a look at today's lesson. So today's lesson is solving trig equations day 2. And we're going to be looking at a few different things. If you recall on day 1, our answers were for all solutions, right? The general solution, like the plus, pi n or whatever the period happens to be. Today we're going to do a little bit of a different thing. We're going to look for solutions on a particular interval. So that's the difference for today. One of the differences is we're going to focus in on one particular interval. So we're going to have a finite number of answers, not an infinite number like with all solutions. Okay, so let's kind of start. Let's just kind of jump in. We want to find all solutions on the interval 0 to 2 pi. So with this particular one, I'm going to go through a way to do this that you should be familiar with from Algebra 2. Let me just kind of remind you right here. So think back to Algebra 2. If you had something that looked like this, just something like that, the technique that you would use, you recall, where you squared both sides? Remember that? That's the technique that we're going to use here. We're going to square both sides. Do you remember the problems that we had when we squared both sides? Yeah, and possible extraneous solutions, right? When that technique, squaring both sides, many times, that's probably half the time, causes an extraneous solution. So we're going to use this technique because the squares of these guys, the cosecant squared and the cotangent squared, they're related to each other, right, with the Pythag identities. And so I'm going to be able to turn one into the other if I do this technique. But I just need to be careful. I'm going to have to check my answers. Okay, so just a little bit of a warning. Just want to remind you where we had accomplished this before. This was the type of problem that we used this technique on, where we squared both sides. So I'm going to move the cotangent over. So I'm just going to rewrite it. Okay, and now I'm going to use the technique of squaring both sides. So I square the left side and I get cosecant squared. I square the right side and I'm going to have to FOIL that, right? So it'll be 1 plus 2 cotangent plus cotangent squared. Okay, so I just squared both sides. Alright, so my decision is, do I turn the cotangents into cosecants or the cosecants into cotangents? And so since I have a single first power cotangent, I really want to turn the cosecant into the cotangent. Okay, so I'm going to use Pythagorean identity on cosecant squared. And cosecant squared is 1 plus cotangent squared. Okay, so now I'm just going to combine like terms, get it all cleaned up. You see the cotangent squareds are going to divide off, and the ones, right? The ones are going to go away. So I'm basically left with 0 equals 2 cotangent x. I divide the 2 off, and I get 0 is cotangent x. So now I need to think about where cotangent is 0. So cotangent is cosine, right? Cosine over sine. So we need to think about where cosine is 0. And so that would be at pi over 2, right? Cosine would be 0 here and here. Right, pi over 2 and 3 pi over 2. Okay, so now we're going to need to check. We're going to need to check our solution and see if both of those are correct. When we check our solution, it's going to be important for us to go back to the original, to the untouched one. Go back to it and plug the numbers in and see if it works. So that's what we're going to do. So cosecant of pi over 2 minus cotangent of pi over 2, is that 1? Okay, so let's do that. So we get, let's see, cosecant is the reciprocal of sine, right? Sine at pi over 2 is 1, so cosecant will be also cotangent. So cosine over sine. Cosine at pi over 2 is 0. Okay, and so that is true. Pi over 2 works. That's a solution. All right, let's try 3 pi over 2. So cosecant of 3 pi over 2 minus cotangent of 3 pi over 2, is that 1? All right, so let's do that. So cosecant is the reciprocal of sine. Let's see, sine at 3 pi over 2. What is sine at 3 pi over 2? That's -1, right? -1 minus cotangent at 3 pi over 2. So cosine at 3 pi over 2 is 0. Okay, is this true? That is not true, is it? That is not true. So 3 pi over 2 is not an answer. It's an extraneous solution that was created by the technique that we used. So we really just have, well, let's talk about this. Well, what 3 pi over 2 doesn't work, so that we really just have that one solution. Our interval is 0 to 2 pi. So finding out, generating both these solutions, discovering that 3 pi over 2 doesn't work and crossing it out, that's going to be part of your work, right? You're going to get points for that. If you don't do that, then you won't get those points. Do you have to show all this? No, you can do it in your head if you want to. I'm fine with that. But we need to recognize that these two are possible solutions and then recognize that one of them is not. Does that make sense? Okay. All right. So students will usually ask, well, oh my gosh, am I going to have to check every single problem? Well, I mean, if you want to live dangerously and just kind of run with it, you'll be fine most of the time. 90%, 90+% of the time, all the solutions you get are going to be right. So I guess if you want to live dangerously, no, you don't have to check. And I'm not going to make you check anything. That's your choice, whether you check it or not. I would really encourage you to for sure check when you're doing this technique where you're squaring both sides, because like half the time you're going to get an extraneous solution. But if you don't use that technique, most of the time you're going to be just fine. But it just depends, how much time you have to check. Is it valuable to check your answers? Sure. Sure it is, because then you know if you're going in the right direction or you've done something completely crazy wrong. But I'm not going to make you. So I do want to discuss that. It's a good idea. Really important with technique like that. Okay. So the next problem. Oh, this is a great problem. Okay. You remember probably a month or so ago we had this really fun lesson on linear combinations. Remember that? See, the memory was not coming back in the other class either. They're looking at me like, what are you talking about? Linear combinations. Okay, I'll start writing the formula up there for you. Maybe as I write the formula, your memory will start to kick in, and you will remember. Remember, it was b cosine x plus c sine x is equal to a cosine. Remember this lovely formula? X minus d, where we found a. I guess I need to write that. I know, I see some memories are coming back. Yay! A, remember, was the square root of b squared plus c squared. Remember that? And d, so now we're starting to remember, yes, d was arctangent of c over b. It's back. Remember, when I taught, we learned this, I think it was Unit 2. I'm not for sure. There's a whole lesson recorded on this if you need to go back and look at it. I think it was Unit 2. I was like, yeah, this is a great one, and we'll see it later, and you probably just ignore that part, see it later part. Or maybe you just was like, sure. Here's the time where we see it later, right now. Because on a problem like number 2, this formula is going to make our lives easy. Working it without this formula would be, I don't know. I wouldn't want to try it without the formula. So let's kind of demonstrate how it works. Just remind ourselves, this is the old formula, and this is how you get the A and the D. Okay? And so let's walk through it. Let's convert it. So our B is 1 and our C is root 3. Right? So our A, and I'll go ahead and write it out. A is 1 squared plus square root of 3 squared. Right? I'm using this to convert to this formula. Cosine of x minus. The D sometimes gave us trouble. What's quadrant we're supposed to be in? What's it supposed to be like? So let's kind of do some little scratch work over here. We're looking for arctangent of C. It's the sine one over the cosine one. The sine coefficient over the cosine coefficient. Root 3 over 1. One of the issues that we had when we learned this is figuring out what quadrant to go to. Remember that? We were having trouble with that. If my x value, my x coefficient is positive and my y coefficient is positive, which quadrant am I going to be in? The first quadrant, right? Quadrant 1. I need to be in quadrant 1. So I need a quadrant 1 angle where arctangent, or where tangent would be root 3. That's what I need. Remember, tangent is sine over cosine. So we need sine to be root 3 over 2 and cosine to be 1/2. So let's think about that. We want sine to be root 3 over 2, so that means the y value is taller. And we want cosine to be 1/2. We see where that would be? Pi over 3, right? That would be pi over 3. And that equals root 3. This is just a little scratch work. Okay. Are we okay? So now I'm going to isolate the cosine. This, 1 squared is 1, square root of 3 squared is 3, 1 plus 3 is 4. You with me? So that's just square root of 4 is just 2, or that's a 2. So we're going to have cosine of x minus pi over 3 equals root 3 over 2. Okay, so now before we really want to jump in and start expanding it using a subtraction property, really, we rarely are going to do that. That just makes it makes it gigantic. Okay, instead we're going to use the technique that we talked about where we cover this part up, just kind of ignore it. Right, we want to see where is cosine root 3 over 2. Just think unit circle, just unit circle. Where is cosine root 3 over 2? So that's going to be where cosine is longer, right? So the x is longer right there and here. Right, that's where cosine is root 3 over 2. These two locations. So I take the argument and I set it equal to, so cosine is root 3 over 2, where at pi over 6 and negative pi over 6, right? That's the location where that's true. So now I'm going to take my argument, x minus pi over 3 equals pi over 6, or my other possibility is x minus pi over 3 would be negative pi over 6. Okay, those are my two options. So I add the pi over 3 over, going into, I guess, sixths. So x is going to be, so what would this be? 2 pi over 6, right? 2 pi over 6 added over, I get 3 pi over 6, which is 3 pi over 6 would be pi over 2, or x could be, and add that over. So let's see, pi over 3 would be 2 pi over 6. Move that over and I get pi over 6. Okay, those are my options. Now, I need the interval from 0 to 2 pi. And I know that the standard period for this is 2 pi. Right, so we need to think general solution, though you don't have to write the general solution. You need to think about it because you're going to have to fill all this interval. So if I add 2 pi to pi over 2, it's going to take me outside the interval, right? So I don't need to worry about that. If I add 2 pi, again, outside the interval. So I really do only have 2 solutions. Okay? We okay with that? Okay, last one. So the interval we're looking for is from 0 to pi. So we need to really pay attention to the interval. We want to capture all of the answers in the interval. So I need to isolate the cosine for x. So get that by itself. So I have cosine for x, and I want it to be positive, of course, so I move that over. I get 1/2. So I'm going to use that same technique. I'm going to look to see where would cosine be 1/2. Cosine would be 1/2, and it's positive, so where it would be the x value would be shorter, right? So like this. Okay, so what would that be? That would be pi over 3 and negative pi over 3. Alright, so our technique, recall we set the arguments for x equals pi over 3, or now let's think about, I use the negative rotation, but I don't have any negative, negative is not my interval, so maybe it would be to my benefit to use the positive rotation. So let's think about, if I went all the way around this way, what would this be? It would be 5 pi over 3, right? So I'm going to use 5 pi over 3 instead, or 4x equals 5 pi over 3. Okay, so I want to multiply both sides by 1/4. Right, so x is going to be pi over 12, or x is going to be, multiply by 1/4, 5 pi over 12. Now, something to note here, really important. This right here, remember from, I don't know, Unit 2, period equals 2 pi over b. Remember that? Okay, so b in this case is 4. So 2 pi over 4, or pi over 2. Okay, so the general solution would be pi over 12 plus pi over 2n, 5 pi over 12 plus pi over 2n. So let's think about this practically. I'm in 12, so let's turn pi over 2 into 12s. What would that be? 6 pi over 12. Okay, so we're going to look at that. 6 pi over 12. If I add 6 pi over 12 to this, am I going to get a number in this range, an angle measure in this range? I am, aren't I? Right? Because 1 pi over 12 plus 6 pi over 12 would be 7 pi over 12. Is 7 pi over 12 inside here? What would pi be in 12s? 12 pi over 12, right? So that's what we're looking for, right? That's what I need to do with fractions. I need to make it so it makes sense, right? 12 pi over 12. So if I do 1 pi over 12 plus 6 pi over 12, I get 7 pi over 12. That's definitely in here, right? 0 to 12 pi over 12. I have to include that solution, or I'm going to, lose part of my answer. So let's start writing out. So it's pi over 12, comma 5 pi over 12. And then we just said if I do pi over 12 plus 6 pi over 12, I get 7 pi over 12. That's definitely in the interval. What about if I add 5 pi over 12 to 6 pi over 12? That's going to give me, that's in the interval also, isn't it? That's 11 pi over 12. Now I'm at 11 pi over 12 and my interval cuts off at 12 pi over 12. Do you think I'm going to have any more? No. No, so these are all of my solutions. We need to be careful to include all the solutions in the interval. Does that make sense? Are we okay?